Hi, I'm going to show you the project 4, how to create triangle waves of variable frequency with the Dragon 12 light board. So here is the Dragon 12 light board, and here's my analog discovery 2. So I'm going to be able to read the waveforms using this device, and we'll also be able to hear the waveforms because I'm using DAC B to create them. And then I've moved my jumper to DAC B so that it connects the output of DAC B to the input of the speaker. So as I'm doing these, you'll hear the tone created by that triangle wave, as well as you'll be able to see the triangle wave on my desktop. So you see I'm running my messy room. This thing just has power going to it. I can just hit reset and create triangle waves for 10 seconds, input frequency in hertz, to hit the pound key if the input's less than 7 digits, and then set the frequency. So I'm going to set the frequency over here so I can show you the waveforms app at the same time. So running this, just kind of have a frequency display, it's just some garbage. We're at 10 milliseconds per division and 5 volts per division. So 0 to 5 volts, right? So we expect some kind of triangle shape. So over here, I'm going to first start with 500 hertz, just a good, easy waveform. You can hear that, see it on the display, and also you can see that it's calculating 498. Very good value, very low error. Now that ends after 10 seconds, so the user is able to just input a new frequency without having to hit the reset button. So let's go ahead and now, just to show a different value, we'll do that, cut that in half. So you heard that 500 hertz tone, so now let's check out a 250 hertz tone. So lower pitch, you can see the triangle wave and the frequency there. Very cool. Let's go to the bottom of our range. So, well, there's a couple of things. Well, anyway, we'll go to the bottom of our range. We'll do the 2 hertz. So you can't really hear it. You might hear the clicking, but you can see that that is a 2 hertz waveform, right? The 1.99, yeah. Now let's do a 1 hertz. You might hear the clicking, and then, so 1 hertz behaves poorly. See, not a really perfect triangle, but 2 hertz behaves very well. Yeah, and so that, let's zoom in a little bit and then do that again. So right, because it's calculating the frequency across this whole spectrum. So unless we can fill that, see, we get that 2 hertz there. Let's see the repeated. Yeah. Okay. Right, so you see that 2 hertz. Really perfect. Okay. Do the 1 hertz. And it's, it is like 1 hertz. Like you see that 1.1.9. It's just, it kind of has these discontinuities to it. Okay, let's jump up to a higher frequency. Start with 1000 hertz. So really clean 1000. Now, what's really cool about this is it's all the waveforms run for 10 seconds. So even though the waveforms are faster and slower, and we create one period at a time, we're able to scale it and run them all for 10 seconds. So that was 1 kilohertz. Let's jump to 2 kilohertz. So we type in 2000, hit pound. You can hear that. You see, this reading is good. Very low error. Beautiful triangle. Okay. Now let's jump up to are we going to try and do the extra credit project? No, I am not. Let's jump to do 10 kilohertz. The sine wave is much more difficult to figure out. So there's 10 kilohertz. You can see it's 9.7 K, right? So pretty close, not exact, but kind of a rough looking triangle, still cool. Then let's jump to 16,000. Nice, look at that triangle. Whew. You can't even, I can hear it just a little bit. It's very like weird high pitch humming. I don't know if you'll be able to hear that, but that's there. So, and then let's see, let's go to 25,000. You're gonna be like, what? 25,000? No way. Yes way. So, kind of rough, not exactly, but 23 kilohertz triangle wave. Yep, we got to 25,000. Ooh. You hear that? Let me hit reset. Maybe it didn't like the 25,000. 25,000 is, so I'm going to show you in the code, but the theoretical max, but with how the code works, is 50,000. So I'm going to go ahead and do that. And you can see, yeah, really faint. Can't hear it at all. You've got a waveform kind of like this, something like a triangle wave at that frequency. So awesome. How does this work? So let's look at the code here. So take our user input, display our messages. Okay, this is the main thing that we're doing, this code here. So we have a certain number of levels. This is based on the homework solution to homework 2 number 5, I think. It was the one where we're supposed to create a 10 hertz triangle wave. That was where we had a forever while loop that nested 3 inner for loops to create a single period. So I've adapted this so that we've got 2 for loops to create a single period instead of the 3. So this first for loop creates the negative slope, and the second for loop creates the positive slope. You can see here I've also changed this. This was 9 FFFF, and I've changed it to AFFF, and this one to A000. So it outputs to DAC B instead of DAC A. I've also changed how these numbers work. So instead of dividing by 50,000, we divide by levels, which is scaled by the user input's frequency, which is interesting. So 50,000 gives us 10 hertz. Yeah, I believe it was 5,000 was here, and that was for 10 hertz. So 50,000 divided by 10 gives you the 5,000, and so that actually ends up working. So we tested this, and you can see that it works for the frequencies, but it scales in that way, which is very cool. One thing that's different is that this is 4095 instead of the, I think, 1020, it'd be 1023. So that is that way because we aren't doing any right shifts, right? So FFF is 4095, right? So instead of like only going up to 1023 and trying to fill or delete these three Fs, we have to go all the way to 4095 so that these Fs will clear, and so here all the way to 4095 so that we can fill these with Fs. And then that gives us, the max, that's the max value for the DAC and the min value for the DAC. Now this is a little misleading in how I'm explaining it because there's only 1023 levels to the DAC, but there's those 2 extra bits that we don't care about, but we still need to fill, and so in terms of like the efficiency of its algorithm, this is like a more efficient way of generating this algorithm rather than having to do like left shifts to get the values in the correct spot, right? Anyway, and it works, so that's cool. So each of these for loops these 2 for loops together create a whole period. So this outer loop decides how many periods we want to create. And what's really cool about that is frequency is in terms of periods per second, right? How many periods happen every second. So if we want it to happen for 10 seconds, we just multiply 10 seconds times the periods per second, and that gives us the total number of periods, or the total number of these loops that we need to do. So that's how we do that. So this could be 5. It could be any number of seconds that you want the tone to exist at. So it would be really cool. You can turn this into a function that outputs you could say create triangle, and your first argument is frequency, and your second argument is the runtime in seconds, right? And you can go down with that. Yeah. That's the main thing for how this code works. That's the main algorithm of it. Okay. Well, anyway, that's it. Thank you. Bye-bye.